Hello class, welcome to this video on AP Statistics. So we're chapter 3 review. So we're looking at part 2, we're looking at lesson 3.2. So continuing on, the first set of problems are about making predictions. Number 17, a random sample of 45 books is selected from the library. The number of pages and the weight of each book is recorded. The relationship between the number of pages in the book X and the weight of the book in ounces Y is modeled by the equation. What is the predicted weight for a book with 425 pages? So here, the predicted weight, that's your y hat, right? So all we got to do is just plug in the x equals 425 into that y hat equation, right? The regression equation. We got 2 plus 0.035 times 425. Okay, so we can go ahead and plug that in there. And we could do that using our graphing calculator. We got 2 plus 0.035 times 425. So we get a predicted weight of 16.875 ounces. All right, so we want to identify and interpret the slope. So remember that this is the y-intercept, and this is the slope. 0.035x, or 0.035 is the slope, and y-intercept is 2. So so the slope is 0.035. So let's first identify that. That's b. And remember, the invisible denominator is 1. Now remember, slope is rise over run, so it's y over x. Now the y is the weight, right? So it's 0.035 ounces. And then the x is the number of pages. Okay, so this is going to be 0.035 ounces per one page is what it boils down to. And so for each additional page, the predicted weight of the book increases by 0.035 ounces. Okay, so that's how we're going to interpret it. Okay, so for each additional page, the predicted, now you have to include the word predicted here, weight of the book increases by 0.035 ounces. All right, that's the interpretation of the slope. Now we're going to identify and interpret the y-intercept. So the y-intercept, remember, is when x is equal to 0. So if I plug in 0 into that, I'm going to get 2 for the predicted weight. So what that's saying is that if there's a book with 0 pages, then we would expect that it would weigh 2 ounces based on the model. Okay. Does that make sense in this situation? Well, the answer is yes, it makes sense. If you just have a book with no pages, then we're just talking about everything else, right? So you have, in the book, you have the binding, you have, all that stuff, and then you have the pages, right? So it's just saying that the base weight of the book is 2 ounces, and then if we add pages on there, it obviously increases the weight. All right, so the y-intercept is 2 ounces. And this is saying a book with no pages is predicted to weigh 2 ounces. By the regression model. Which makes sense if you are describing the binding of the book with no pages added. So essentially, if you're describing the binding of the book with no pages added at all, then it makes sense. Having a weight does make sense if you have no pages. Okay, so number 18. it says, at the end of the semester, a math teacher wonders if a student's attendance has an impact on the final exam scores. Here's a scatter plot that shows the number of days absent and the final exam score for a random sample of 10 students. We've seen data like this before. What is the approximate y-intercept of the regression line, and interpret this value? Okay, so you can see based on the regression line drawn that the y-intercept is there, right? That's the y-intercept. So the y-intercept is about 90. So that means that A is approximately 90. Okay, so the y-intercept is approximately 90. And so what it's saying is that, okay, so interpret this. A student with no absences is predicted to get a score of 90, right? On the final. Okay, so that makes sense. And in part B, it says the slope of the regression line shown is negative 2.75. So that's my B value. Interpret this value. So again, that's negative 2.75 divided by 1. Now, this is the 1 on the bottom is the x. So this is the 1 absence. And then this negative 2.75 is the percentage score, I guess, if you will, right? 90%. Or yeah, I guess, yeah. I'm just going to put points here. It could be percentage points, or it could just be points, right? So in this case, for each additional absence, we would expect that the predicted score for the final exam is going to decrease by 2.75 points. That's what we're saying, okay? So for each additional absence, the predicted final score decreases by 2.75 points. Okay, again, you make sure to include the word predicted, and then for each additional, and then decrease by how much, right? All of this stuff is required, but definitely include the word predicted. Don't omit the word predicted here. All right, part C. Use the regression line to predict the final exam score for a student with 4 absences. All right, so in this case, we got our y-hat model is A plus bx, and A is 90. So A plus bx, and here b is negative, so we're going to write this as negative minus 2.75x. So that's our regression line model. And then we're going to predict the final exam score for 4 absences, so 90 minus 2.75 times 4. All right, 2.75 times 4, that is 10. So we would predict that their score is, we have a score of 80. All right. Actually, I don't know. It's actually not 10. Let me double check that. 2.75 times 4 is actually more than that. It's actually more. I was thinking about 2.25. So that's 90 minus 11, which is 79. Okay, so we would predict that their score is about a 79 for part C. For part D, the student with 5 absences scored an 80 on the final exam. Did the student score better or worse than what would be predicted using the regression line? All right, so there are a couple ways that you can answer this question. You can look at the regression line and see that the student that had 5 absences had a score of 80. That's this point right here. That is above the regression line, which means that he did better than what was predicted. You can also use a regression line to calculate that. So we got y hat. So we can say y hat of 5 absences is equal to 90 minus 2.75 times 5. If we calculate that, we would get 76.25, which is less than 80, which means that the student actually scored higher than what was predicted. Okay, so that takes care of number 18. So let's go to number 19. The scatter plot shows the vehicle weight in pounds and highway fuel economy in miles per gallon for 15 different trucks. A table shows computer output from a linear regression analysis on the data. Okay, so write the equation for the regression line. Be sure to define any variables that were used. Okay, all right, so we got our constant coefficient. This is my A, and then my weight coefficient, that's my B, okay? So remember, y hat equals A plus bx, right? All right, so we got the y hat equation equals A plus bx. Now b is negative, so we're just going to put minus. All right, there's our equation. Now y hat is equal to the predicted highway fuel economy. Okay, in miles per gallon. And x is the weight of the truck. In this case, the weight, the weight of the truck. In pounds. All right, so part B, it says, what is the value of the correlation of the relationship? So here they actually, they don't give you the R, but you can find the R from the R squared value. Okay, so the value of the correlation is equal to the square root of the R squared value. However, remember that this is a negative relationship because the coefficient is negative, right? And so that means the R is going to be negative. So we're going to do the negative square root of R squared. Okay, so the R squared value is 0.427. All right, so we're going to calculate that. Square root 0.427. So we get 0.653 for my R value, but it's going to be negative, right? Okay, so there's my R value. Remember, the sign matters because it's a negative relationship, so it's got to be negative. All right, C, the GMC Sierra weighs 4,400 pounds. Predict the highway fuel economy for the GMC Sierra using the regression line. All right, so we got y hat of 4,400 pounds is equal to, so we just got to plug it in for x. Okay, and remember this 4,400 doesn't mean this 4,400 means that I'm plugging it into there. Okay, so when we write the y hat model, sometimes we'll write it as y hat of x, right, equals A plus bx. That's simply what I'm writing. Okay, when I write the 4,400 next to the y hat like that. All right, so we can go ahead and plug that in. Okay. All right, so it's 24.567 miles per gallon. Okay, so that's the predicted highway fuel economy for that vehicle. About 24.5 miles per gallon. The GMC Sierra had an actual highway fuel economy of 29 miles per gallon. Calculate the residual for the GMC Sierra. So it was actually 29. So remember, the residual is equal to, let me just write it out, residual is equal to y minus y hat. So the actual is 29, but the predicted was 24.567. And so we have a positive residual, which means we underpredicted, which means that the actual value is over what we predicted. So if I subtract those, I get 4.433 miles per gallon. All right, so there you go. So that's number 19. So we'll go to number 20. It says the relationship between height in feet and weight in pounds for a random sample of polar bears is modeled by the equation given. The largest polar bear on record was found in Alaska in 1960. He was 12 feet tall and weighed 2,210 pounds. Calculate and interpret the residual for this polar bear using the given model. All right, so I'm just going to call this y, and I'm going to call this the height x, okay? And, it's weird that they wrote it like that instead of the traditional, so I'm just going to rewrite it the traditional, statistics way. So it's a plus b x, okay? So that's the a plus bx. All right, so large polar bear, it says, okay, so the height of the polar bear was 12 feet tall. And remember that the height is given in feet, so we're good. So we can plug it in. Okay, so let's plug it in. So y hat of 12. So we're plugging in 12 feet. Okay, so plug that in. So we got negative 3250 plus 475 times 12. So 2,450 pounds was the predicted height. So that means that if the actual height was 2,210 pounds and we predicted it to be 2,450, that means we're going to have a negative residual. That means we over predicted, meaning that the actual height was less than what we predicted. So our residual is equal to y minus y hat is equal to, the actual was 2,210 pounds, but the predicted was over that. So it's going to be negative 240 pounds. And we want to interpret it, okay? So the interpretation is that the actual weight of the polar bear was 240 pounds less than the weight predicted by the model for 12-foot height. Okay, in other words, we over predicted. Okay, so it's just another way of saying we over predicted it. The actual weight is less than, which means we over predicted it. All right, number 21. Susan is the head of human resources at a small business. To ensure that employees are being paid fairly, she records the number of years' experience and the current salaries of the employees at the company. She creates a linear regression model to fit the data. Selected values are shown in the table along with the equation for the regression model. Okay, so they actually give us the equation. Again, we'll use y for that, and we'll use x for that. What is the residual for an employee with 7 years of experience? Okay. So this is the actual y value, and we need to calculate what the y hat is going to be based off of the y hat equation. Okay, so the y hat equation is the 45,769 plus 1,209x, right? And now we're going to plug in 7 into that. So we're going to plug 7 into that equation and get a value. Let's do that over here. So $54,232 was the salary, right? That was the predicted salary. But then their actual salary was $57,500, and so the residual is equal to that number minus the prediction. Okay, so we got 57,500 minus 54,232, which is $3,268. Okay, so that's the residual. Use the model to make a prediction for an employee with 10 years experience. Okay, so we're just going to make a prediction. So y hat of 10 equals, and then again, we're going to plug in 10 into our equation. Again, I'm just going to show my work. And then this one is make a prediction with 30 years of experience. Okay, so if I plug that in, again, I'm just going to do this and just change that number to 10. And then I'm going to repeat that and change that number to 30. All right, so those are our two predictions, $57,859. And this one's $82,039. Okay, so those are our predicted salaries. Now it says for the next part, which prediction should be trusted more, the prediction for 10 years or for 30 years, and why? Well, if you look at the data, we only have data from 3 years up to 16 years. We don't have anything before 3 years, and we don't have anything after 16 years. And so we would expect that the 10-year prediction would be, let me just go back to it. So we would expect that the 10-year would be more accurate, right? Because we actually have, that's actually within the data that we collected, right? It's between 3 and 16 years, whereas the one with 30 years, we don't have, that's outside of our data set that we collected. Okay, so in other words, part B is an interpolation, part C is an extrapolation. Okay, so we're going to say the prediction for 10 years is more trustworthy, or well, let's say it should be trusted more. Let me just put it should be trusted more. Because 10 years is within the range of values collected for years of experience. When creating the regression model. In other words, it's an interpolation. The 30 years is outside of the this range. And therefore, or we'll say and therefore outside of the linear trend. Okay, so this is an extrapolation. Okay, and the main idea is that by extrapolating outside of the data set, 30 years, we're implicitly assuming that the data is going to remain linear at that point in time. But we're actually not, we actually don't have enough knowledge to know that that trend is going to continue past our data set. We only know that within the data set that we collected, the trend appears to be linear, but we don't have the foreknowledge to say, okay, well, outside of this, I can predict that it's still going to be linear. We actually are not sure. It could be curved for all we know, but within our data set, it appears to be linear. And so you're making those assumptions when you're making that prediction. And so that's an extrapolation. All right. So as used cars are driven more miles, they tend to lose value. This is known as depreciation. For a random sample of 150 used cars recently sold, the linear regression model given relates to cars' mileage and its sales price Y. What is the estimated decrease in sale price that corresponds to an increase of 50,000 miles? Now, estimated decrease in the sale price. So in order to do this, we could look at our slope. Our slope is B. And it's saying, okay, well, it's expected to decrease by negative $0.2, in other words, 20 cents, for every mile driven, for every 1 mile. All right, so it's decreasing the price of 20 cents for every mile driven. Well, then in this case, if we have an increase of 50,000 miles, then we're going to multiply this by 50,000 miles, right? And so how is that going to affect the price? Well, it's going to be, 20 cents times 50,000. So in that case, it's expected to be, 20.20 times 50,000 is 10,000. Let me double check that. 0.2 times 50,000. Yeah, so it's 10,000. So $10,000. So we'd expect that the price would be decrease, a $10,000 decrease. So it's got to be A. All right. So number 23, a linear regression model was built to predict the test scores out of 100 of students based on the number of hours they studied. The regression equation is given, where y hat is the predicted score and x is the number of hours studied. A student who studied for 8 hours achieved an actual score of 75. What is the residual score for this student? Okay, so it says study for 8 hours, so x is equal to 8. So we're going to plug in 8 here. 30 plus 5 times 8, which is 40 plus 30 is 70. So they got a score of 70, but they said this is the predicted score. However, the student actually scored a 75. So the residual is 75 minus the 70. And so the residual is 5. So the answer is B. All right, now we're looking at residual plots. So before we're looking at predictions, now our focus is going to be shifted more towards residual plots. Of course, it's going to be a mixture of stuff from predictions because you need to make predictions in order to calculate residual plots. But there will be more of an emphasis on residual plots. But here we go. A country's natural resources, including oil, gas, and coal, can greatly impact the country's overall economy as measured by the GDP, the gross domestic product. So listed on the table are the 8 countries with the most revenue from natural resources and billions of dollars, along with the GDP and billions of dollars. So using technology, find the least squares regression line relating the revenue from natural resources and the GDP. Be sure to define any variables that you used. Okay. All right, so let's get the regression line equation. First, I'm going to reset my memory. So I'm going to hit second plus, and I'm going to go down to 7 for the reset. Reset my memory because I already entered data from earlier. So I want to erase it. So I'm going to erase all my RAM. I'm going to go to reset. All right, now the RAM's been cleared, so we can go ahead and type in the data. So here we're going to say that, okay, so we're going to say that the GDP, the natural resources is going to influence the GDP, the gross domestic product, right? If you look in here, it says that the natural resources can greatly impact the overall economy measured in GDP. So this is actually going to be X, right? Natural resources is X and GDP is Y, okay? Because the X influences the Y. The natural resource influences the GDP. Let's go ahead and go to stat, edit, list one is going to be my X values. So these guys, 30, 16.3, so on and so forth. And then for the Y, we're going to enter 106, 54.6, and so on. Okay, so we went ahead and plugged in the values. So we got the natural resources here. We got the GDP here. So we got all the data. So now we're going to quit out of this. We're going to go to stat. We're going to go to calculate. We're going to go to linear regression, number 4. L1 is X and L2 is Y. So we're good here. Just go down to calculate. All right, so now we got our y hat, x hat. So let me put this over here so we can write down, write down our values. Remember, be very careful. The A and the B are switched here. So it's going to be y hat equals A, this is going to be my A in the equation, plus the B, X, okay? So the A is going to be negative 2.96, when we write this out, okay, or negative 2.97. We're going to round it. Okay, so we got y hat equals negative 2.97 plus 2.93 x. Okay, and then we got to define what it is. X equals natural resources in billions, and y hat is predicted GDP, again in billions of dollars. All right, so that's our y hat, or least squares regression using technology. Using the least squares regression line to use it to predict the GDP for a country with a revenue of $50 billion. So that means that x is equal to 50. Okay, so we're going to plug in 50 into this model. Okay, so we plug that into there. Okay, so we get 143.53 billion. $143.53 billion. All right, so that takes care of number 24. Okay, number 25, the amount of sugar in grams and the number of calories in a 12-ounce serving of 10 different popular soft drinks are shown. The scatter plot with the least squares regression line and the residual plot are shown. So we got the least squares regression, we got our residual plot. This is where the residual stuff starts to come into play. The sum of the squared residuals is 221.9. First off, what is residual? Residual is y minus y hat. So when they say the sum of the squared residuals, what they're saying is they're taking the sum, or adding the residuals squared. And they're saying that that is 2219.9. That's what they're saying. Which point contributes the most to this sum? Well, the one that's going to contribute the most is the one that is the farthest away from the regression line, right? Which is going to be this point right here. So this point is going to contribute the most because that's the farthest away. The residual here is greater. So this is a high residual. And therefore the residual squared is going to be greater. Okay, look at that. That's a pretty big square, right? Whereas from here to here is not as big of a square. From here to here is not as big of a square. The one with the biggest square is that one. All right. So the point at approximately 54, and that looks to be around 210, will contribute the most. Because it has the greatest, or the largest residual. From the regression line. Okay, all right, so part B is a linear model appropriate for this data. So this is where we look at the residual plot. Well, we look at both. So the scatter plot, this doesn't appear to be very linear if you look at the data, right? But I mean, you might say, okay, well, maybe it is linear, but we just, it's just a little bit off. Well, if I look at the residual, now you see a pattern in the residuals. You see a clear pattern. We shouldn't see any patterns in residuals. It should be random, right? There shouldn't be any up, down, up patterns, anything like that. Any U-shaped patterns or anything like that. If there's a clear curved pattern left over in the residual plot, then that indicates that it's not appropriate to use that model, right? So not appropriate since there is a leftover curved, I'll put that in parentheses, pattern in the residual plot. All right, so that's what we're looking for. Randomness in a residual plot enables us to say that it's appropriate. Otherwise, it's not appropriate to use that model. All right, so let's look at number 26. The scatter plot shows the mean annual precipitation. Okay, right over here. Okay, oh, here we go. Mean annual precipitation in centimeters and the mean annual temperature in degrees Celsius for 21 different forest regions. All right, so we got 21 different different data points for annual temperature and then annual precipitation, and we got our computer analysis right here. Describe the relationship between mean annual precipitation and mean annual temperature. So we're going to describe that. We'll do it over here since it's going to take some space. Remember, describe strength, direction, form, and unusual features, right? So clearly it's positive based off of this trend here, and it seems to be moderate. It's not very strong, so we'll say moderate. There is a moderate, positive, and here they're indicating that's linear, a linear relationship. Between mean annual precipitation and mean annual temperature. Unusual. So there appears to be an outlier, one that is far away, like really, really far away. There's a possible outlier for sure over here, because look how far away that is from this line compared to, for example, this. That's not as far away, right? This one's not as far away, although it is still pretty far away here, but it's not atypical, right? This one's the most far away as far as from the line itself. So this one is about the same distance as that. So that seems to be kind of like typical, right? But this one seems to be most far away. When we're talking about the vertical distance, okay? So there is a potential outlier at around 250, and this is about 14, 15 maybe. It's around there. I'm just gonna say 14, but it might be about 14, 15. All right, so that's the description. Write an equation for the least squares regression line. Be sure to define any variables. Okay, so now they give us the computer output. So this constant, this indicates our A, this indicates our B. All right, so y hat equals 10.303 plus 0.053x. That's our equation, okay? X is equal to mean annual temperature. Y hat equals predicted. Oh, this is precipitation, sorry. So X is precipitation and Y hat is temperature. All right. Part C, wet tropical forests are designated as areas with 140 to 220 centimeters of precipitation per year. Create an interval for the predicted mean annual temperature for these forests. Okay, so the interval is going to be based off of this. Okay, so 140 to 220. So we're going to make interpretations for 140, or predictions for 140 and 220. So when X is equal to 140 versus X is equal to 220. All right, so our Y hat here, I'll just call it Y hat 1 for our first prediction, for our first thing, is 10.303 plus 0.053 times 140. And then I'll call this y hat 2. All right, and we'll get two different values here. All right, 17.723 degrees Celsius, because we're talking about temperature. And we're going to repeat this, but change this 140 to 220. 21.963. All right, so the interval is from 17.723 degrees Celsius to 21.963 degrees Celsius. Okay. All right, so hopefully that makes sense. Now let's look at the next question. So looking at 27, the scatter plot shows the total annual revenue in billions of dollars for the social media website Facebook for each year from 2010 to 2022, recorded as years since 2000. All right, so if I look at this appears to be exponential or something like that, something curved. So yeah, it appears to be curvilinear, non-linear. So that's what we see so far. Just a quick observation. But it says the least squares regression line for the relationship is given. So they give us this equation of this line here that they've drawn. Calculate and interpret the residual for the year 2016 if the actual revenue was 27.64 billion. So this is the Y, that's the actual. And then it says interpret the residual for the year 2016. So this means that the years after 2000, that means X is equal to 16, right? 16 years after the year 2000. That's what X represents. So 16. All right, so let's go ahead and plug it in. So Y hat equals negative 121.89 plus 10.33 times 16 for X. See what that is. So get 43.39. All right, and then we're going to subtract that from 27 point, or yeah, we're going to do Y, subtract that from 27.64. So the residual equals the actual minus that. And that should give you a value of negative 15.75. And that's in billions. Okay, so there's a residual. So the actual, so they want us to interpret as well. So the actual revenue was $15.75 billion. This is the decimal right here. Less than or below what was predicted. What was predicted revenue for 2016. Okay. All right, so let's take a look at part B. Without any calculations, use the scatter plot and the graph of the least squares regression line to estimate the residual for the year 2021. So without any calculations, use the scatter plot and the graph to estimate the residual. Okay, so the residual, and so no calculations, we're just gonna estimate. So for the year 2021, that's when X is equal to 21. So when X is equal to 21, the estimated was about 90 billion. And then over here, there's a data point that actually is 21, 120. And this point is 21, 90. Now this 90 is our Y hat. This is our y. So our residual is y minus y hat, so 90 or 120 minus 90, okay? Or 30 billion. Okay, so it appears that it's about 30 billion. It might be like 20. It might be in the neighborhood of the 20 to 30 billion range. We're just estimating, okay? So if we said, okay, this is about 90, this is at about 120. It might be a little bit less than that. It might actually be closer to, yeah, it's actually closer to 115. So it might be actually closer to 115. So let me do that, just to be a more estimate. So it's about 115 minus 90. So we'll say it's about 25, okay? Again, it's an estimate, so it's fine if you didn't get exactly that. So about 25 billion. So part C, sketch a residual plot for the data on the axes given by approximating each residual. All right, so we're gonna approximate the residuals and then graph it. Okay, so here for 21, we get a residual of about 25, right? Okay, so let's look at 22. Let's do 22. So 22, we get, so let me get rid of these. So 22, we get this value, which is, might be about 100, and this value here is about 110-ish, a little bit over 110. So it's approximately 10 for that residual. So we'll say it's approximately 10 for that, for 22. For 20, let's go ahead and do 20. 20 is a very small residual, so 20 is actually close to 0. So we'll say that it's pretty close to 0. 19, let's do 19. 19 is pretty small. This is about a little bit over about 75, and this point is about 70. So maybe about 5, maybe perhaps. So, but less than that. So I would say close to 5 for 19. 18, let's see, 18 is right here. That's about 55-ish. This here is about 60, so that's actually more closer to 5. So we can make that one closer to 5. And it's 5 negative, right? Because if the y is below the line, it's, if the dot is below the line, then it's negative. If the dot is above the line, it's positive. Okay, 17. Let's say that's about close to 40, and here is close to 55. So maybe 10-ish, 10 to 15. And then we'll look at 16. A little over 40. And that's about 25, so that's about 15 or close to it. So put it like around here. And then 15. 15 is about the same distance as this one, so it's gonna be pretty similar to the 17, but so pretty similar. Again, we're just estimating this, but I'm gonna try to be okay, you know, a decent estimate. So here, that's about 10, that's about 22, so about 12-ish maybe for 14. Let's just say around negative 12, negative 11, negative 10. Now we go to 13. So 13 is getting close. So this is about 12. This is about 10 or 8, so it's about 4-ish, maybe 4 or 5. So I'll put it around here. And then 12, 11, and 10 are above. So this is going to be pretty close. So this is going to be just above it, perhaps. And this here, if I continue this pattern, if I continue the linear trend, then this is at negative 10, maybe negative 10, negative 5. And then this is at around 5. So that's a difference of 15-ish. So we'll go around here, 10, 15. And here, this is like negative 20 or something like that over here. Oh, we're doing it for 10. So let me do it for 10. So 10 is like here. Oh, that was for 10. And then this one is for 11. 11, yes, that was 11. For 10, it's going to be about negative 20. And yes, it's going to be about 20-ish. So it's even bigger. Okay, so it looks kind of like this. So again, this is just an estimate, predicted amount. So there's our residual. There seems to be a curve pattern. So, and that indicates that if there's a leftover pattern, that indicates that the model is not appropriate. So the correlation of the relationship is 0.95. Is a linear model a good fit? So this is what we were saying. No. Although R is large, the linear model is not a good fit because the residual plot shows a leftover curved pattern. All right, so if there's a leftover pattern, that indicates that it's not a good fit. The linear model is not a good fit. Okay. All right, so number 28, at the end of semester, a math teacher wonders if a student attendance has an impact on final exam scores. So they select 10 students and record the number of days absent in the exam score. So we got computer output and a residual plot. So is the linear model appropriate? All right, so notice this is random. This seems to be completely random, right? Up, down, up. You know, it's just random. And you see roughly, you know, we got maybe 3 points here, whatever. It doesn't. We would expect it to be 50% above and below, but notice that there's a little bit more above than below, and that's fine because these 2 points are actually almost on the line, right? Whereas these 1, 2, 3, 4, 1, 2, 3, 4, 5, these 5 are directly above the line. These 3 are directly below, and then you have 2 that are on it. So really you have 50% above, you got 30% below or on the line. So that means 50% is actually below or on the line, right? Or near the line. So the percentages are not too much of a big deal. What we see is that there's randomness. That's the main idea, is that there's randomness in the residual plot. So in this case, we're going to say yes, there is a random scatter on the residual plot, or there is randomness in the residual plot. In other words, there is a lack of leftover pattern. There's a lack of pattern. On part B, what is the actual exam score for the student with 5 absences? Round to the nearest whole point. Okay. Well, how do we get the actual exam score? Well, remember, residual is y minus y hat, and y is the actual. So the actual is equal to y hat plus the residual. All right. So that's how we can do that. Now we can calculate y hat because we know what the regression line is. Okay, so the regression line, according to the computer output, is 89. Let me zoom in a little bit. 943x minus 2.755. 0.943 minus 2.755x. So that's the regression line. So we're going to plug in 5 absences into that. So let's do that first. All right, so let's go ahead and plug into that. Do that over here. So 76.168. Okay, 76.168. So that's for 5. Now, then we want to find the residual. So let's put that here. Plus, we're going to add a residual. So for 5 absences, if we look here, oops. Okay, so if we look at 5 absences, it appears that we have a residual of about 4-ish, right? If you look at there, that looks like about a residual of 4. Okay, so that means we're going to add a residual of about 4 to that. And so that's about 80.168. Okay, so it's approximately a score of 80. Okay. All right, so that's their actual exam score, or approximately. All right, so now let's look at number 29. Emily works as a customer service representative answering customer emails. For 8 days, she records the amount of time she spends answering emails and the number of emails she can answer during that time. Her results are shown in the scatter plot with the least squares regression line and the residual plot. Okay, so on the amount of time spending, the number of hours worked, and then the number of emails answered. So it seems to be, one positive relationship. We look at the residual plot. Okay, so residual for 3 hours is 4.5. Interpret that value. So we just got to interpret it. It's positive, so that means that if it's 4.5, that means that the actual is greater than, right, what was predicted. So we're going to say that the actual, now this is 4.5 emails, right, because the number of emails answered. So the actual number of emails answered is 4.5 emails more or above, you can say more or above, more than the number predicted for 3 hours by the regression line. All right, that's how you would interpret that. Or in other words, if it's more than if the actual is more than, that means we underpredicted by 4.5. The residual for 4 hours is 0. Explain what this means. So if the residual is 0, then that means that what was the actual is actually the same as what was predicted, right? So is equal to what was predicted for 4 hours by the regression line. Okay, here's a list of each residual rounded to the nearest tenth. So we got 2, 4, 6, 8 residuals for the data points. The mean of the residuals is 0, and the standard deviation of the residuals is 4.017. Interpret this standard deviation. All right, so now, standard deviation of residuals, what is that? The formula for that, the standard deviation of residuals is equal to, the standard deviation of residuals is the average of the residuals. So it's the average residual, essentially, meaning the average distance between what we predicted and what was actually occurring, right? That's essentially what standard deviation is telling us, that the residuals vary by X amount from the mean, or from the X amount from the prediction, right? Okay. All right, so here, let's go ahead and do that. Now the mean of the residuals is 0 because when we add these up, you're going to get 0, right? When you add up those positives and negatives, you're going to get 0. And then divide that by how many you have, it's still going to get 0. That's why the mean is 0. All right, but let me just show you the formula. The formula for the standard deviation is of residuals is the square root of the sum of the residuals squared divided by n minus 2. And so what this is telling you is it's telling you the average of the squared residuals, or the average of the residuals rather, right? It's the average of the residuals. The average distance from each value to the regression line. All right, so in this case, we're going to say, the residuals typically vary. So on average, the residuals vary or are different from the mean of 0. You can say from the mean of 0, or you can just say that they typically vary from the regression line, right? For the regression line by about 4.017 emils. Okay, so that's how you interpret the standard deviation. The residuals typically vary by about 4.017 emils. All right, so now let's look at number 30. A student records the amount of protein in grams and calories per gram per serving in 14 types of cheeses and butters. The output shown in the table is from a least squares regression line, least squares regression to predict the amount of protein from the number of calories. One slice of American pasteurized cheese has 79 calories, 4.7 grams of protein. Based on this, the residual, does the regression model overestimate or underestimate the amount of protein for this type of cheese? All right, so they're saying that the amount of protein is 4.7. That's the actual, that's the Y. But if we compare that to the regression model, now the regression model is y hat equals 1.575 plus 0.032x, right? Based on, that's my A, that's my B, because A is my constant. And then if we plug that in, if we plug in y hat 79 calories into that, so then y hat of 79 so let's plug that in there. So you get 4.103 grams. And so if if this is the predicted 4.103, this is the actual. So that means we underpredicted it. We underestimated, right? We underestimated. If we calculate the residual is y minus y hat. It's going to be a positive value. 4.7 minus 4.103 is positive. It's greater than 0. If the residual is positive, that means we underestimated, right? So in this case, the answer is A. All right, 31. Scientists compared the maximum weight in pounds and average life expectancy of 16 dog breeds. Let X be the average life expectancy of the dog breed, Y be the maximum weight of the breed. They give you the least squares regression line. Suppose all the values for maximum dog weight were converted from pounds to kilograms. 2.2 pounds in a kilogram. Which of the following give the equation of the least squares regression line for the updated data with X equals average life expectancy, Y equals maximum weight? Okay, well, if we converted from pounds to kilograms, that means we have to divide by 2.2 pounds because there's 2.2 pounds in a kilogram. So we're going to need to divide everything here by 2.2, right? So that's exactly what we're going to get. So let's see what we get. So 329.4 divided by 2.2. And then we get 21.6 So 149 and 9.8. So it's got to be B for this one. 149.73 and 9.82. They're both going to change. If you change the units, both of them are going to change accordingly. The answer is B. All right, so now we're looking at outliers, high leverage points, and influential points. This is still technically part of lesson 2. Lesson 2 is the meatiest lesson of the bunch, which is why this video is going to be longer. But here, let's go look at 32. Consider the following scatter plot. Classify each of the 2 marked points, A and B, with any of the following descriptors that apply. Okay, so this is where most of the data lies, along this line. And then if we look at A, it's really far away in the Y direction. Now, if I look at this, the Y bar, X bar seems to be around here, the average in the X's. The average in the Y's seems to be, right around here. So, we're just guesstimating. So A is really close to that, but A is close to this is the X bar equation, by the way, and this is the Y bar. So A is really far in the Y bar direction, but it's not very far in the X bar direction. So it's not very far as the in the X direction, which means it's not a high leverage point, because high leverage points are points that are far away in the X direction, either really big X values or really small X values. Okay, so that's something to keep in mind. So in this case, point A is a vertical outlier because it's far away in the Y direction, but it's not a horizontal outlier. Okay, high leverage means outlier in the X direction. Okay, so in this case, point A is a vertical outlier. Now, an influential point, it's not a high leverage point because it's not a outlier in the X direction. It's not a horizontal outlier, in other words. However, an influential point is a point that includes outliers. So outliers are influential points. An influential point is something that is going to affect the correlation and or the y-intercept and or the slope. So in this case, what's going to happen for A is that A is going to tend to pull this line up because it is above the line and it's close to the X bar line. So it's just going to pull the line up, right? So it's going to affect the y-intercept, and obviously it affects the correlation because it's far away from the data. So we're also going to say it's an influential point. Now let's look at point B. Point B is far away from the X bar. It's an outlier in that direction. And so we would expect that to be a horizontal outlier, right? And because it's a horizontal outlier, that means it has high leverage. So it's also a high leverage point. And because it's an outlier to begin with, and it's high leverage, all that stuff, it's also influential because what B is going to do, since B is far away in the X direction, what it's going to tend to do, it's going to tend to have a swinging or pivoting motion of the line. It's going to tend to pivot the line. It's going to swing this line, the right end down, and it's going to swing the left end up. And so it's going to change the slope. It's also going to change the y-intercept. Okay. So in any case, it's an influential point. Okay, so hopefully you understand the meaning behind these different terms. Again, if it's influential, it's going to affect a bunch of stuff, which means it's going to be an outlier. So if it's an outlier, it's an influential point, vice versa there. But not all outliers are high leverage, right? Some outliers are just vertical outliers, in which case they're not a high leverage. All right, so number 33. The scatter plot below shows the weights in pounds and the gas mileage in miles per gallon for 9 different vehicles. A least squares regression line is also shown. Estimate the coordinates of X bar, Y bar, where X is the weight of the vehicle in pounds and Y is the gas mileage in miles per gallon. Mark the point on the scatter plot. Okay, so here we can guesstimate that, right around here is the average, maybe like around here is the average. So we're just kind of going to guesstimate maybe 25 and a half or 26. And they say to mark the point on the scatter plots. We'll just kind of mark it here in red, X bar, Y bar. That seems to be about the halfway point, right? If you look at the data. Okay, so the point seems to be about 4,026-ish, approximately. If the point 4,021 is added, so 4,021, so let's mark that in green, 4,021. So if we added a point there, well, it's right on the X bar line then. That means it's going to have a pulling motion. It's going to pull this line down, right? So if it pulls that line down, then the y-intercept is going to be impacted, right? It's going to be decreasing the y-intercept. Okay, so it would decrease the y-intercept. Now, if the point 4,021 is added, how would the slope be affected? It's not going to impact the slope as much. It's not, because, in fact, it's not going to impact it really much at all, if at all, because it's just pulling this line down. So it's going to be pulling it like this, and the slope is going to be about the same. As long as it's close to the X bar, it's not going to really touch the slope. If it's far away from the X bar, then it's going to be an influential, or it's going to be a high leverage point. And a high leverage point will impact the slope. It'll impact the y-intercept, right? And a bunch of things. But it'll definitely have a swinging motion if it's far away from the X. So in this case, the slope is gonna be approximately the same. All right, so number 34, consider the following scatter plot. What effect does the point at 85, 86 have on the correlation between X and Y? So 85 and 80, so let's estimate the X bar, Y bar. So let's say the X bar, the average in the X's, let's say it's around here-ish. And then the average in the Y's, let's say is around here. Just kind of got to guesstimate there. We got X bar, Y bar. Now, so yeah, let's make it more like 50. All right, so, well then in this case, let me just make this a little bit like this. All right, well in this case, we can see that if I have 85 and 86 added here, so 85 and 86, that's this point right here. So what's that going to do on the correlation? So actually, the regression line is right around there. So this point is a high leverage point because it's far away from that. But what it's actually going to do is, because it's high leverage and it's in the same trend as the line, it's going to strengthen the correlation. So it's actually going to strengthen it, even though it's a high leverage point. It will, since it's close to the line, it's going to strengthen that relationship. So it would make the correlation stronger. Or closer to 1. All right, so now let's look at 35, the Daytona. So we should be almost wrapping up lesson. Let's see, we got a few more questions on here, I think, before we wrap up. Okay. All right, so let's add 35. The Daytona 500 NASCAR race is a 500-mile car race drive, or car race. Not surprisingly, the driver's average speed is correlated to the length of time it takes for them to complete the race. The average speed and finishing time of 500 winning drivers has a correlation of negative 0.538. The mean and standard deviation of the average speed are given. Mean and standard deviation of finishing times are also given. Find the equation of least squares regression line. All right, so the formula for, so remember, it's y hat equals a plus bx. Now to get b, it's the correlation times the standard deviation in the y over the standard deviation in the x. And to get a, we'd have to do y bar minus b times x bar. All right, so my r is negative 0.538. Let me move this over. The sy is given. Sy is 19.4, sx is 11.3. So we calculate the b, we can calculate the a, y bar minus b x bar. So let's go ahead and calculate our b first. (19.4) divided by 11.3. So negative 0.92. Negative 0.924. And we're going to plug that into here for b. Okay, and they told us our y bar and our x bar. So y bar is 197.3 minus the b that we got. Now this is a double negative, so minus negative. So it actually turns into plus. And x bar is 150.5. So this turns into a plus. We can just turn it into addition. 197.3 plus 0.924 times 150.5. Get 336.362. Okay. All right, we're going to keep it to 3 decimal places. So y hat equals 336.362 minus 0.924x. There's our regression. All right, so now let's look at, oh, that's it. That's all they want us to do for that one. Sorry, I thought they wanted more than that. Okay, so we got the y hat equation for that one. Number 36, consider the following data for players at the linebacker position at a recent NFL combine, where x equals the 40-yard dash time, y equals the player's number of reps at the 225-pound bench press. Okay, calculate x bar and y bar. All right, so we're trying to see if there's a relationship between their 40-yard dash time and their bench, right? So that's what we're looking for. So we'll say this is x, this is y. So let's calculate x bar. So x bar is equal to 4.39 plus 4.43 plus ... all the way to 4.64 divided by 2, 4, 6, 8, 9 players that we track data on. And y equals 29 plus 25 plus ... plus 14 divided by 9. Okay, so we don't have to write down all the values, we just have to write down a few. So here we get 4 point something. Now we're going to show you how to do something here. We're going to show you how to calculate, get statistics for these. So we're going to actually put them into the calculator here. But before we do that, we have to make sure we delete our memory. So we're going to go down to reset, all RAM, reset. Let's go to stat, edit, and let's type in our data, 4.39 and so on and so forth. And so that'll be our X. All right, we're going ahead and typed in the numbers. Okay, so we got the X 40-yard dash time on the L1. L2 is the 225-pound bench press reps. So we got that. So now next I'm going to quit out of that. So second mode. I'm going to go to stat and I want to go to calculate. I'm going to do two variable statistics. So I'm going to do that. 2 variable statistics so we can get X bar, Y bar. X list is L1, Y list is L2. Yeah, we can go down to calculate now. And okay, so it gives us our X bar, 4 point something, 4.508. And then we go down to Y bar, we get 21.333. So we'll do the 3 decimals here, okay? So our X bar, he said it was 4.508. Y bar was 21.333. All right, good. That's our X bar and Y bar. Using X bar and Y bar from part A, explain why this equation can or cannot be the equation of least squares regression line for this data. Now, it must be noted that for any regression line, no matter what the regression line is, for any least squares regression line. The point y bar, x bar has to be on that line. It can't be above it, below it, or anything like that. It has to be on that line. So if the x bar and y bar is not on the line, that means it cannot be the least squares regression line. The least squares regression line must contain x bar, y bar. Okay, that's key here. So does this model that they give here contain that? Well, let's find out. So we're going to plug in the x bar is 21.3 or 4.508 into it. Okay, so let's plug in x bar equals 4.508. Let's plug that in as our x value. So y hat equals 4.508. All right, so we got 310.523 minus 57.394 times. Now we're going to plug in the x bar into it. And we should get 21.33, the y bar. If we do not, then that means it's not on that line. It cannot be the regression, the least squares regression line. Okay? So let's calculate that. We get, let's quit. So we get 310.523 minus 394 times 4.508. All right, look at that, 51.79. Let me make sure, yeah, 51.7. Okay, so 51.79, which is greater than 21.333. That means this point that we have is below the line. Like the regression line is saying that it's 51.79, right? The regression line is saying it's here, 51 point something, but the y bar, x bar is down here at 21.33, right? That means it's not on the line, so it cannot be the least squares regression line, okay? So bottom line, it has to be equal for this to be on the regression, the least squares regression line. So no, this could not be the least squares regression equation because it does not contain x bar, y bar on the line. Or yeah, because it does not contain x bar, y bar. We can just say that. It does not have x bar, y bar. All right. Okay, so that's a good point to make right there. Number 37, the number of calories and the fat content in grams are shown in the following scatter plot for, this should say 10 major brands of hot dogs. The equation of the least squares regression line is given. If the outlier at 8012 is removed and a least squares regression line is calculated, which of the following must be true about the new slope? Okay, so we got 8012. This is the outlier potentially, right? This is the outlier that you're saying. If it's removed, the key here is if it's removed. So it's already there. So if it's, so normally, if that, normally this would have a pivoting motion. It would, if it's not included, it will, it's far away from the x bar, so it's going to have a pivoting motion. It's going to pivot this up and pivot this down, right? Normally, if it wasn't there to begin with. But here, it's saying that it's already there. So if I remove it, then it's going to have an opposite effect. It's going to instead move this back down and shift this back up. And so what that's going to do is that's going to make the y-intercept decrease, right? And it's going to make the, let me put this in red, the new one, and it's going to make this right side go up. And so that's going to tend to increase the slope. So it's going to make it steeper. So it's going to be greater than what you would say? Well, this is the slope originally. So the new slope is going to be bigger than that. So the answer here has to be C. All right. Should be 38. 38 should be the last one before we get to lesson 3.3. All right, good. So this is the last question for this, for lesson 2. A random sample of 12 casual runners was selected. For each runner, the number of hours they run per week and the resting heart rates and beats per minute were recorded. The scatter plot displays the resting heart rates versus the number of hours run per week. Also shown is the least squares regression line. And here's the residual, or the, let's see, or not residual plot, sorry, scatter plot. This line looks pretty flat right here. But this is a scatter plot of resting heart rate and time spent running. It says point A is an influential point, so this is influential. A new least squares regression line will be calculated when it's removed. How will the removal of the influential point affect the new least squares regression line for the remaining 11 points? All right, so what will happen? So remember, normally this guy, if he weren't there, if that point was not there, he would, or that point would, since it's far away from the X bar, right? Most of the data is there. It's far away from that. It's going to have a pivoting motion, right? It's going to make it pivot closer to that, up towards it, and then pivot this down. However, by removing it, then it's going to have the opposite effect. So it's going to pivot this down and pivot this up. So then it's going to go like this. So that means the slope is going to increase. The slope is gonna get steeper. Let's just say it's gonna get steeper, and the y-intercept is gonna increase. In this case, the slope will now be negative because it was about 0 here. So now the slope will be negative. All right, and then the y-intercept will increase. So in this case, we're looking for the best solution. The y-intercept will not decrease, so it can't be B. Y-intercept will, no, the y-intercept will not remain the same. The y-intercept, no, it can't decrease. Y-intercept will increase, slope will be, slope can't be positive, slope is going to be negative. Okay, so the answer is D. All right, guys, that's going to do it for the video. Hope you found this useful and informative, and I'll see you in the next one. The next part 3 will be lesson 3.